At this part of the presentation, I'm going to talk about modeling transient stability of grid-forming converters equipped with current reference limitation. I will talk about challenges and proposed solutions. The materials of this presentation is extracted from the following two papers. One of them is accessible from IEEE Transactions on Power System and another from Archive. At first, I will talk about the definition of transient stability of GFM IBRs, and then effect of current saturation is investigated. We will see that the current saturation causes shrinking domain of attraction, and our proposed solution, which is model predictive control, is then introduced. Another challenge, which is the existence of saturated stable equilibrium point, is also reviewed. And then we will see that set of returning angles, which is the set that the grid-forming converter comes back to the normal operation mode, might not be complementary of the set of entering angles, which is the set that grid-forming converter goes to the current saturation mode. And this is another challenge which will be addressed at this presentation. And then the talk will be wrapped up by a summary. Transient stability is defined to ability to retain synchronism after a large disturbance. This large disturbance could be a fault or a large phase jump, for example. And the key variables which are related to the transient stability of a GFM IBR is angle and frequency of its active power controller. If the APC is designed as a virtual synchronous generator, virtual inertia, and droop control, it follows the second order swing equation, as you can see here. There is the power angle curve similar to what we had for synchronous generators for GFM IBRs. And these power angle characteristics is entitled with two equilibrium points. One of them is a stable equilibrium point, delta zero. A deviation from the stable equilibrium point is compensated with the negative feedback to bring it back to the stable equilibrium point again. However, there is another equilibrium point which is unstable equilibrium point, which a deviation from that is unstable and it doesn't come back. And if the grid-forming converter's angle passes the angle of unstable equilibrium point, it will become unstable. At the right side, you can see the phase portrait and the border of transient stability for a grid-forming converter. As you can see, everything is until now is similar to synchronous generators. So you might ask, why are we studying transient stability of GFM IBRs? It's all the same as synchronous generators. However, there is a big difference. When grid-forming IBRs face a large disturbance, they easily go to the current saturation mode because they cannot tolerate high amount of overcurrent. In the normal operation mode, the current output of a GFM IBR is the difference between the voltage of its terminal and the Thevenin voltage of the grid divided by the Thevenin impedance of the grid. And this current is acceptable below the maximum current in normal operation mode. However, if there is a voltage sag, or if there is a big angle between the local reference frame and global reference frame, then this current becomes more than the allowable amount. Therefore, the grid-forming converter transits to the current saturation mode. This transition from normal operation mode to the current saturation mode can be modeled as the inequality that you can see here. If cosine of delta is less than an expression which is a function of voltage of the grid and impedance of the grid, then it goes to the current saturation mode. So it means that the delta, which is the angle difference between local reference frame and common reference frame, is more than a threshold. And this threshold is dependent on both voltage and grid strength, which is the impedance of the grid. When the grid forming converter transits to the current saturation mode, the voltage of the D frame is not following its reference, because if it could follow that reference voltage, then it wouldn't go transit to the current saturation mode. It cannot follow, then it transits to the current saturation mode. And when it's in the current saturation mode, the output current, instead of being adjusted by the voltage controller, is adjusted by the saturation block and give it the current saturation amount to the grid. If it's, for example, I with the IMS max with the angle of beta, then the voltage at the output of the grid forming converter follows these two formula. You can see that now the angle delta, which is the angle between a local reference frame and the voltage of the grid, does not represent any physical meaning. However, it should be stable. This angle, even though it's not representing any physical meaning, it should be stable during a disturbance because it gets affected by physical quantities and it affects the physical quantities. How it affects the physical quantities? Through these two formula. As you can see, delta has effect on VD-sat and VQ-sat. Therefore, it affects the voltage and subsequently it affects the active and reactive power output of the grid forming converter. And it gets affected from the physical variables through the APC, active power controller, because the input of the active power controller is still the active power, which is a physical quantity. Therefore, these angle, even though now it's totally virtual and in the controller and does not represent any physical meaning, should be stable. When the grid forming converter transits to the current saturation mode, the relation between the output power and the angle of the APC changes. You see the blue curve is the power angle relation in the current saturation mode, and the red one is the power angle relation in the normal operation mode. Because of this change of the power angle relation, first of all, the angle of the unstable equilibrium point decreases. And another effect is that the deceleration area also drastically decreases. Therefore, it causes shrinking the domain of attraction of transient stability. Here, the blue line is the border of the domain of attraction for the with the current saturation, but the brown one is the domain of attraction if there is no current saturation. Here we can see three examples to illustrate on how current saturation shrinks the domain of attraction. Case A is a case that the angle of the current saturation is minus 30 and post-fault delta is 62.01, and you can see that this trajectory is stable. However, if the angle post-fault angle increases up to 67.71 degree, then it becomes unstable. And in the right side, you can see that for current for the unstable case remains in the current saturation mode, but in the stable case after delta comes back to less than an amount, then it comes back to the normal operation. In case C, there is no current saturation block, and even though the after fault angle is more than case A and case B, but it's stable. However, being stable in case C needs a high amount of overcurrent. Here you can see that it's more than 4 times of nominal current, and it's really undesired, because if you want to eliminate the current saturation mode, you should over design the converter to be able to tolerate this amount of overcurrent. So there will be a huge over design cost. But if you don't go for that huge over design cost, you should deal with the current saturation. You should accept that there is a current saturation, and this current saturation is shrinking the transient stability. Now propose a solution that kind of solve this issue or make this issue less um, important, less dangerous. The solution that we proposed is a model predictive control. Uh, this model predictive control adds two corrective signals to active power controller. One of them is the change in the active power reference, and another is direct phase jump in the active power controller output. And the former changed the frequency directly and angle indirectly. The latter changed the angle directly. So these two signals provide full controllability over the trajectory of the grid forming converter after the fault. And these two signals are optimized based on model predictive control. This MPC is formulated as minimizing the deviation of angle from the angle of the stable equilibrium point, subjected to two sets of constraints. One of them is modeling the dynamic of GFM IBR in both current saturation and normal operation mode, and another set is the safety limitations, for example, not going below the desired frequency or not absorbing power from the grid. This is another set of constraints. Since this MPC is a mixed integer nonlinear programming, it's not easy to find its domain of attraction, and it's really complicated. One thing that we have done for estimating the conservative domain of attraction is that we choose one control law that we know it's feasible, and then if this feasible law is um, stable for a region, then the MPC would be stable for that region as well, because MPC is the optimal one. This is just one heuristic out of many possible solutions. Here we can see if delta Pref max, which is the corrective active power change, is big enough, then the domain of attraction increases up to the delta zero crossing sat. And delta zero crossing sat is the angle after which the grid forming converter absorbs power from the grid. So this is not desired to go after that. So this domain of attraction is increased until the desired point. You might ask why we are using MPC instead of this control law. This control law is very simple. We can use it without need of any optimization solver, but we went for the MPC. This is the question that you might ask. I want to engage you to this presentation and ask you that what do you think about it? For example, if you ask this question, that why we are using CL0, why we don't use CL0 instead of MPC? What would you answer? Feel free to unmute your microphone and answer if you have any opinion about it. Any answer? So now I tell you this is because this control law CL0, even though it gives good domain of attraction, but there is no constraint on safe trajectory. Therefore, the trajectory might go in an under frequency situation because you are imposing minus delta Pref in the whole time that it is in the current saturation mode. But when you are using the MPC gives the corrective signals as much as needed without kind of approaching the limitations. This was one challenge, shrinking the domain of attraction and the solutions we have talked about. Another thing is Another challenge is existence of saturated stable equilibrium point. The P delta curve in the current saturation mode has an intersection with P0, which is stable. This is when the curve in the current saturation mode is increasing. And there is the possibility that after a large disturbance, the grid-forming converter converges to this stable equilibrium point. Even though theoretically this stable equilibrium point is stable, but it is not a desired stability. It makes the grid forming converter works in an operation mode which is not desired. You want grid forming converter comes back to normal operation mode and act as a voltage source. But if it converts to the saturated stable equilibrium point, it continue working as a current source. This is an example of converging to the saturated stable equilibrium point. For two cases which the post-fault, post-disturbance angle is the same, but the angle of the current saturation is different, there is two possible trajectories. In one case, which is beta is -6 degrees, the grid forming converter comes back to the stable equilibrium point and continue working as a voltage source. However, in another case, which beta is -90 degrees, it converts to the saturated stable equilibrium point. And another challenge is that the set of angles at which the grid forming converter comes back to the normal operation mode is not complementary of the set of angles that grid forming converter enters the current saturation mode. The reason is that the current reference generated by the voltage controller in the current saturation mode is a function of voltage error in the current saturation mode. So because the reference which is compared with the maximum value is generated by voltage controller. In the current saturation mode, the error which is given to the controller is dependent on the situation in the current saturation mode, the voltage error in the current saturation mode. Therefore, there might be situation that this uh, voltage controller generates a reference less than the allowable value, then it goes to the current normal operation mode, and then it comes back to the current saturation mode, goes there, come back, goes there, and come back. Or there might be situation that the grid forming converter go to the normal operation mode later than what is expected. In order to give some intuition about what I'm talking about, I will give an example out of the power system, just something to illustrate. Consider that there are two rooms, room 1 and room 2, and you are working in room 1. When their room 1 is very hot, you go to room 2, which has different set of air conditioning. You go to room 2, and in room 2 you wait until the room 2 becomes colder than than a threshold. You don't know the whether the temperature of room 1 when you are in room 2. Based on the condition, the temperature condition of room 2, which has a different system, you will guess that whether the weather of the whole area has been cooled or not. However, the uh, room 1 and room 2 temperature are not simultaneous. So there might be situation that you are in room 2 and you feel cold and you guess that okay, room 1 is also became colder. You go to room 1 and you realize that no, room 1 is still warm. You go to room 2 and you oscillate between these two rooms because you came back sooner than what was expected. Or there might be situation that the weather of the environment, the temperature of environment became less than the threshold, but in room 2 still the temperature is not less than that threshold. So you didn't recognize that the room 1 might be cold enough that you can go into that. The same thing would be correct for transiting between grid forming between the current saturation mode and to normal operation mode. We have proved that this set of returning angle is a function of the angle of the saturated current. Hashed area in this figure is the set of returning angle, and field area is the set of entering angle that grid forming converter goes to the current saturation mode. Naming the set of returning angles as R and set of entering angles as S, if delta is in R minus S, which means the hashed area which is not filled, then it no operates in the normal operation mode. If the angle of the grid forming converter is in S minus R, it operates in the current saturation mode because it is in the angle of it's in the set of entering angles, but it's not in the set of returning angles. So it would work in the current saturation mode. If it's in both of these two sets, which has been shown as a hashed area in this figure, which is filled as well, it oscillates between these two modes. And if it's out of both of these two sets, the area which is not filled and it's not hashed as well, it keeps its previous mode no matter what. This is what happens when the two sets are not complementary. At some angles, for example, here you can see there is an angle that near to 70 degrees that these two sets are complementary of each other. At that angle, it's either in the current saturation mode or normal operation mode, and it doesn't oscillate between them. But other angles, these kind of situations like oscillations might happen. And this oscillation induces a high frequency oscillation to the grid because now your grid forming is transiting between these two modes and sending the current and active and reactive power based on transiting between these two modes. So this disturbance is sent to the grid as well. So at this talk, we saw that the current saturation causes the domain of attraction to shrink. And also we saw that a modular predictive control can enhance the transient stability of grid forming converters. And the existence of a saturated stable equilibrium point in addition to other equilibrium points has been observed. And we saw set of returning angles and set of entering angles are not complementary. And if the angle is in the intersection of these two sets, it oscillates between these two modes. Many thanks for your attention.